Everybody knows this part. Wi-Fi password is about to go away, so if you needed the Wi-Fi password, write it down. So what I'm about to do is actually give an example of this, which is the type A example. It's sort of the simplest example with some beautiful combinatorics that's very easy to understand, and which of course people, if you're familiar with cluster algebras, you'll recognize as also being the type A combinatorics from cluster algebras. Example, my cluster category can be a boundary-derived category of the path algebra of an AM quiver, and of course it doesn't really depend which AM quiver I take, they're all direct equivalent. Portioned out by double suspension and have I got that? Yeah. Okay, thanks. Okay. And in here, so the indecomposable objects correspond to.
So I think it should be maybe -2 or -7.
Yes. Okay. That was what I was worried about. But yes. So yeah. You know what? Minus. But that's not. Yeah. So the indecomposable objects correspond to diagonals of an n plus 3 gon, and the cluster tilting objects correspond to triangulations. That is to say,
can you write a little larger?
yes. That is to say, collections of diagonals in the polygon that don't cross, and with enough of them, which is exactly n of them, so that they actually define a triangulation of the polygon. Okay, so suppose T is basic. And so T, let's write it. So it turns out that that means that T is the direct sum of n indecomposables. Well, okay, I guess you can define n as the okay, and so in this case, so I assume it's basic, so the indecomposables are all pairwise non-isomorphic, and so I'm going to introduce some notation that I can write the index as a sum. As I said, it lives in the flip rotary group at T, so that just means that we have generators which correspond to these EIs, and so I'm gonna write it as a sum I equals 1 to n of the coefficient of EI. So this is my notation for the multiplicity of EI in this index times the class of EI. So that's just, so this is just the notation for the multiplicity. So this is just topology. Okay, so what can we do with the cluster tilting object? So for any m, we can look at EM, this particular sum n of T. There is a unique way to replace EM by some other object, EM star, not isomorphic to M, and such that T star, which is going to be my notation for EM star plus the rest of the EIs. So I swapped out EM and I swapped in EM star. I want this still to be a cluster tilde function. And what I'm saying is there's one way to do that for each of the EIs. There's one way to swap it out and to swap something else back in. And of course, this is, you can see that on the purely combinatorial level. And because on the combinatorial level, what I'm doing is I'm taking some diagonal of the triangulation and I'm removing it. And once I remove a diagonal from the triangulation, then I have an open quadrilateral left. And now that quadrilateral has two diagonals. And so, of course, I can put back in the one that I started with, but I don't want to do that. I'm going to put in the other diagonal. And so there's one other diagonal, and that is the diagonal that corresponds to the EM star. It's the one thing I can replace EM with, so as to get a different cluster tilting object from the one I started with. And so, given that, it's natural to ask, what happens with the index with respect to T star of K versus, if we started with the index of K with respect to T, how do we find the index with respect to T star? And, if you sort of think about this, I mean, sort of very naively, it might seem like you're kind of doing some sort of a tilt. And you might imagine that, we're just kind of changing bases. Before, we had our basis consisting of the subends of T, and then we swapped out one basis element, we put in another basis element, and we're re-expressing kind of the same thing in a different basis, and so you might imagine that it would just be a linear transformation, but that's not quite the case. But it's not so far off. So to express what actually happens, I need a little bit more notation. So there are triangles in the triangulated category relating EM and EM star. Where B is in the additive category generated by T, but without EM. And similarly, the other way around, there's a triangle like that. B prime also in T with EM. Okay, so in this case, we can write the index with respect to T prime of K. Oh, okay. C T prime T star as above K rigid. We can write the index with respect to T prime of K as, well, let's think of it in the following way. We're going to start with the index of T with respect to K, and that includes summands of this EM, and obviously we have to take note because we're not allowed to have multiples of, we're not allowed to have EM. EM doesn't exist in the flip group group of T prime. So obviously I have to replace EM by something, but it turns out that's all I need to do. So I'm just going to notate that by writing a substitution. So I'm going to replace EM by B minus EM star if EM is in T0, but as I said, it's not linear because in the other case, we replace EM by B prime minus EM star. That's if EM appears in T1. And only one of those EM can only, because K is rigid, EM can only appear in one of these two positions. And so this can also be described by saying that the index with respect to T of K, the coefficient of EM in it is greater than or equal to 0. And in the second case, we can describe that as saying that the index with respect to T of K of EM is less than or equal to 0. Okay, so that is the story for the classical cluster category. The idea, I think I'm not going to try to write this down, but the idea here is that, you know, if you had EM appearing in T0, you can really see what happens to the exchange, to the resolution by saying, oh, I have this EM, but I can't, I need to somehow replace the EM. I'm going to replace the EM by a B that maps onto EM, which maps onto K. But then I also have to add an EM star into T1. Okay, so you can sort of convince yourself why you would want to do these things. Using these triangles and the T resolution you started with to produce T prime resolution. Or my notation is T star. So what's the interest of this? Well, okay, maybe it's just intrinsically interesting. We have this notion of index, and you know we like to understand it. There are some other reasons that it's interesting. So it categorifies the G vector of K in the corresponding cluster algebra. So in particular, you can, if you can use rigid objects. There's a rigid object corresponding to each cluster monomial in cluster algebra, and then you can understand the index in this. Another reason this is of interest is that this G, so the way the G vectors mutate, which we described here, is a tropical version of the way the coefficients in the cluster algebra mutate. So we can sort of see here a kind of tropicalization, and thus in some sense a simplification of the coefficient dynamics for cluster algebras. And a third reason to be interested is that if our cluster category is associated with a surface, then T is associated with triangulation. I mentioned this case of the disk, but it turns out to be more general than that to other surfaces. And then in that case, the way to think about K is that it represents a lamination. That is a collection of curves, non-crossing curves on the surface, and the index describes the shear coordinates, Thurston's shear coordinates for that lamination. So this gives you also a way to think about those shear coordinates. Okay, so that's the classical setup, and
Can I ask a question?
absolutely.
I was wondering, how is the tropical coefficients necessary for this story? Like, are you assuming something on the coefficients, or do you have any, like, do you have frozen variables or this kind of thing?
I don't have, so, well, okay, let me not, let me keep cleaning while I try to answer your question. Well, I mean, I'm trying not to give a cluster algebras talk in some sense. So to say that to talk about G vectors, I mean, so G vectors are sort of most naturally visible in the cluster algebra. Well, I mean, so one way to see G vectors is to work with the principal cluster algebra. But you still sort of can see the G vectors playing a role in a slightly more hidden way in any cluster algebra. The statement I was making about coefficient dynamics is not really, I'm not really making a strong statement about the non-tropical coefficient dynamics. I'm just making the kind of the statement that's probably, well, I'm sure it's familiar to you, that the G vector dynamics and coefficient dynamics are just related by quantization. So if you understand G vectors, and the point of that is going to be that I'm going to tell you an analogous story in a higher dimensional setting where we will see coefficient dynamics, well, we will see something you could describe, I'm going to call tropical coefficient dynamics, and it raises the question, what could non-tropical coefficient dynamics be? I don't have any answer to that question. And does that address? Okay, super. Thank you. Are there other questions about the cluster category story that I'd like people to be more or less on board? Awesome. Super. Okay. So, part 2 is going to be D plus 2 angulated cluster categories. So, what is a D plus 2 angulated category? A D plus 2 angulated category is a category with D plus 2 angles, surprisingly. So, it has a suspension functor and distinguished D plus 2 angles. So if D is 1, then these are really distinguished triangles, and we're in the classical case. But for us, D is going to be greater than 1. So these D plus 2 angles, they're similar to the triangulated story. We have this collection of D plus 2 objects and morphisms between them, and then finally a map to the suspension of the object from the start of the triangle. And I'm not going to attempt to explain the axioms of these D plus 2 angulated categories. And for the purposes of this talk, we really can just think about them as being like the triangles of triangulated categories. So these were introduced by guys Keller and Operon in 2013. And I asked Christoph at dinner on Saturday why he had done this, and he didn't have a completely convincing explanation. He said, well, he said he was just the authors had just been interested to see what could be done, how the triangulated structure could be extended to something more general. They do arise naturally in higher Auslander right theory, as in the work of Yama and others.
Keller had a question. He said, well, I'll just read what he said. He said that you said we're going to introduce something related to coefficients in higher dimensions and was going to call it something. I didn't hear what that something was.
Oh, I'm sorry. So what I'm going to call it tropical coefficient dynamics. And the question, it raises the question, could there be some non-tropical coefficient dynamics? Right. So this comes up in work of Young. It also came up in Bernhard's talk on Saturday. He had a DZ, something that he called a DZ cluster tilting subcategory. That subcategory is D-triangulated or D-angulated. And its suspension functor is not the suspension functor, so it lives inside the triangulated category. Its suspension functor isn't the suspension functor from the triangulated category, from the ambient triangulated category. it's a power of the suspension functor. It's this d minus 2 power of the suspension functor in the ambient triangulated category. And that's a fairly standard way actually to produce these higher angulated categories is as subcategories, triangulated category, and suspension functors are not the same, but one is a power. And Christoph also said that there's some the de-angulated structure is turning out to be relevant in things that I think are related to what came up in our. So let's say that C and sigma is G plus 2 angulated. Finite to Calabi-Yau category. And again, to Calabi-Yau is going to mean the same thing as before in the sense that Hahms from X to Y or dual Hahms from Y to the double suspension of X. And in fact, I'm going to slightly simplify some of the statements. I'm going to assume a little bit more on the category, which I don't entirely need, but just to make the statements simpler, I'm going to assume a little bit more. I'm going to assume that the category comes from a triangular derepresentation finite algebra. And I'm not going to define that, but so yeah, there's some technical assumption to, which gives you a category which gives you the sort of analog of the property of having no loops and 2 cycles, which we know we like in the classical case, but which you don't necessarily have to assume all the time if you just want to sort of make statements. Kind of, you just have to be more careful about avoiding things. So C is going to be C of lambda, where lambda is triangular. The representation finite. So this is some higher analog of hereditary representation finite. So this is really the closest that you could get in this D plus 2 angulated setting to the categories of Y Marchand, right? And so T is a cluster tilting object. If T is rigid, and so you'll see that I'm writing down a lot of the same things that I wrote down before, actually, but they mean something slightly different. And so what's the other property that I want? The other property I want is for all objects in the category, there should be a T resolution. But what should the T resolution be? Before it was a triangle, it's not going to be a triangle anymore, because we don't have triangles. It's going to be a T plus 2 angle. So there should be some resolution. T0, going to K, going to the suspension of TV, of course, with T i's in at T. So it's the same thing as before. And the whole point of the story really today is that everything works exactly the same way once you set it up properly. So we have the same notion of what it means to be a cluster tilting object.
Keller said, what does triangular mean?
Yeah. So it allows us to avoid having to explicitly assume that there are no loops because we just have it. So it's just so far as I believe we say in our paper, I mean, Jeff would be the expert, it's not me, but we say in the paper that we know of no examples of derepresentation finite algebras that are not triangular. but in principle, it isn't guaranteed by the representation parameters.
And he also asked, do you want it to be D rigid? In other words, xi, dt is 0 or I between, not just but T rigid.
I think that is automatic for any objects in here are going to satisfy that property.
Oh.
So we will also have that for the rigid. Okay, so right, so we can consider the index with respect to T. Okay, so this is just going to be class of T0 minus the class of T1 plus etc. In again split group B group of at T, and this has been studied by studied by Jorgensen. A is independent as before of the choice of the D plus 2 angle. So there's a very nice example, which I don't have time to really define properly, but I want to tell you about it anyway, just on the level of what the combinatorics looks like. And it is the combinatorial generalization of the triangulation of polygon model that we saw at the beginning. So it's very similar, well, combinatorially very similar. And so it's the triangulations of a cyclic polytope. So this is an interesting class of polytopes with some extremal properties, some interesting extremal properties. And surprisingly, with their triangulated structure, or the structure of their triangulations is captured by this higher tilting theory. So category, this special particular category is, I'm going to try to explain what all this notation means. So this is the D plus 2 angulated derived category. This is the D minus 1 higher Auslander algebra of linearly oriented AN, and this is the ceremony. So this gives us a category of this type. Cluster tilting objects correspond to triangulations of the cyclic polytope. With dimension, with its 2D dimensional and n plus 2D plus 1 vertices. So you can check if D equals 1, we're back in the classical setting. Perhaps unexpectedly, the indecomposable object, what the indecomposable objects correspond to, well, in the D equals 1 case, they correspond to the edges of the triangulation. And what those turn out to correspond to is the D-dimensional simplices. So D-dimensional simplices in the interior of the polytope. And so there's a lot more that can be said about this. And Shep and I wrote a paper on this some time ago. And Nate Williams has also done a lot more work in this general setting recently. So those are places to go if you wanted to know more about this. So right, okay, so we want to do kind of the same sort of thing as before. We want to think about swapping out some ends and swapping in some ends, and how that is going to work. And it's natural to ask yourself how to do that in the geometrical setting. And if you happen to be familiar with triangulations above dimension 2, then you probably had a guess for what the right operation is, and if so, you're probably right, because your guess would be bistellar flips, and that's exactly what happens. So let me say this. So T is basic. Rewrite T as a direct sum of objects EI, and for each M, EM may be mutable or not mutable. So in some cluster tilting objects, each EM will be mutable, but in any particular cluster tilting object, some of them will be kind of stuck. They won't be mutable. You won't be able to change them. If they're mutable, that means you can replace EM by EM star in exactly the same way as before, and you can do so in a single way to replace it by something that's different and still get a cluster tilting object. And if it's not mutable, that just means you can't replace it. There's no way to swap it out and replace it with something else. And so again, if T star is the mutation of T at EM, in the same way as before we replaced EM by EM star, we want to relate the index with respect to T star of some rigid object K to the index with respect to T. Okay. And the way that works, well, again, there are two exchange D+2 angles. So one of them, which goes EM star to BD to dot 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 to B0 to EM, and the other one which goes from EM to BD prime to dot 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 to EM star. With the BIs and the BI primes in add T with the EM remove. And now we want to do exactly the same thing and sort of, look for our EMs in our resolution and then replace them using one or the other of these. And that, that sounds good, but it sounds a lot better if EM were at the beginning or the end. If EM were kind of in the middle, it isn't so obvious how you would replace, how you would kind of splice together one of these exchange triangles. And the T resolution to get a T star resolution. And the good news is you don't have to, because the proposition EM is mutable as a summand of T if and only if it only ever appears in the T0 or TD positions. So in the extreme positions when resolving rigid objects. And then, now we can say the theorem. So just C, T, T star as of K rigid. Then the index with respect to T star of K is the index at T with respect to K, where we've substituted for EM the class B0 minus B1 dot dot dot, and finally winding up at -1 to the D class of EM star. That's if EM is in T0, or we substitute for EM B0 prime, etc., -1 to the EM star, if EM is in T. So that describes the mutation, but there's something a little bit funny about this, a little bit undesirable if D is even. So what's the bad feature of this if D is even? Well, let me put it more optimistically or more favorably. What's the good thing if D is odd? The good thing if D is odd is that we can distinguish these two cases just by looking at the index. So we really have a mutation procedure that doesn't require that we think that we know what the resolutions are. We have a procedure that allows us to just work purely on the level of the index class itself. Because when D is odd, this means that the index with respect to T of K, the coefficient of EM in it is greater than or equal to 0, and here it's less than or equal to 0. But in the case where D is even, this will be non-negative in both cases. So we won't be able to, so we really get the nicest thing when D is odd, which includes the class coefficient D is 1, because there what we get is a mutation rule that just allows us to look at the index, based on the index, decide which of the two classes we're in, and then carry out a procedure on the index to get the new index. And I'm out of time, so I will stop here. Thank you.
Are there any questions we can?
Is it obvious that this EM cannot be in both T0 and T?
That follows rigidity. Okay, yeah, good question. I mean, in general, I mean, more generally, if K weren't rigid, then you can describe a resolution for K that would involve sort of splicing in both the exchange triangles, some of this exchange triangle plus some of this exchange triangle, to account for the EMs in either end. But because K is assumed to be rigid, we only have to worry about one or the other.
Thank you for that question. Any questions online? Ralph again.
So if you take these higher cluster elements, like you have to find some category and use the shift in the M neutral.
No, I mean that's yeah, I think it really just doesn't feel like that. The Auslander writing translation that naturally appears in these higher settings is not the normal Auslander translation, but it's the tau sub D. So it's some D syzygy kind of functor, and the Auslander writing quiver itself is sort of, rather than in classical cases, made up of, or it wants to be, it's not exactly true, but it wants to be made up of meshes that are just little diamonds. In the higher D setting, it's made up of little meshes, or it wants to be made up of little meshes that are little cubes of the appropriate dimensions. The dimension increases. So I think that the M cluster setting is just somehow not. It doesn't have that feature. And yeah, so I think it's really just kind of a different generalization.
If there are no more questions for the time being, but let's thank you again. Resume at 10:30 on Thursday.